Hello students, this is Brock Skaggs. I'm going to make a second video continuing on the same problem statement that we started on in Axial Loading 3A. Here we're talking about 3B, we're looking at task 2, we're trying to determine the displacement of the green plate here. And so to kind of recap what happened in the first video is that we were after determining the normal stress in each of the sections there. And so that's where we kind of drew our free body diagrams, which we can see below here, road equilibrium equations. By that we were able to find the amount of force that each of the sections of the shaft were carrying, and then now that we knew the internal force carried by each section of the shaft, we knew the cross-section characteristics here, the diameter of the circular shaft, we then were able to calculate the normal stress carried by each section. Okay, and so now we're looking at deformations. Well, I know this green plate's going to move a little bit. So how much does it move? Does it move up? Does it move down? That's really what we're looking at. And so in these type of situations, you're talking about rods that are getting longer or shorter there just under pure tension or compression. Well, the formula that comes to mind, hopefully first, is something that looks like this. The amount of elongation or compression, delta, is equal to FL divided by A times E, where F is the amount of force carried by the member itself, L is the length of the member, A is the cross-section of the member, and E is the modular elasticity, or Young's modulus, basically a characteristic of the stiffness of the material of the member itself here. And so one of the caveats you have to watch out for with this equation is that these three values, the F, the A, and the E here, all have to be constants in whatever length that we're considering here. And so in this case, we can't just take the length as the overall length of the shaft, because you can see the A is going to be changing as well as the F is going to be changing there. And so what do? Well, we use superposition. And so we basically say, well, can I apply this to each of the sections of the shaft and then just add them all up? Sure. And that's basically what we're going to do. We're going to say something like delta is equal to the summation of I equals 1 to some number n of the Fi, Li, all over Ai, Ei. And the idea is in between each of these sections, we have to have constants there. So in any length considered that we look at Li, the F, A, and E here all have to be constants. And so that's where this falls into consideration here. We got three sections here, so it'll have to be I equals 1 to 3, and then we'll have our individual forces areas. They'll all share the common E value amongst them all, but they'll have different lengths as well. And so one other thing before we get too carried away into that formula is this base formula here that we're using is actually derived from something called Hooke's law, which requires the stresses to be below the yield strength of the material itself here. And so that's one of the things I'm just going to purposely go down through here. The material was 1060 alloy, as you can see. The yield strength is 27.8, or excuse me, 27.6 megapascals, and then I'm going to look at the stress values you computed. You can see 3.18 here, 2.04, 16.98, roughly 17 megapascals is the closest we get. That is less than our yield strength, and so we are good. We are able to use this formula here. And so there's actually a third variation that would cover this a little bit more if we had tapering cross-section that would basically take this numerical summation and turn it to an integral, but I won't focus on this in this video. And so let's go ahead and use our base formula to start writing things out here. We're going to have something along the lines of the overall amount of elongation or compression here that we're looking at, which is equal to the displacement of the green plate, right, is equal to the summation from I equals 1 to 3 here of Fi, Li, all over Ai, Ei. And so really that's all it is a fancy way of saying something like, well, I've got F1, L1 all over A1, E1 plus F2, L2 all over A2, E2 plus F3, L3 all over A3, E3. So that's all that summation is really saying, is a shorthand version of this right here. And looking at this, one of the things that I could make my life a little bit simpler was take out the E as far as the subscript on the E, because that's all the same material in this problem. It's all that 1060 alloy material. And so I can say this as equal to 1 over E times F1 L1 over A1 plus F2 L2 all over A2 plus F3 L3 all over A3. I could go one step farther and recognize, hey, each of these A's is going to have a pi over 4 that I could pull out, but I'll just go ahead and write that in. And so now that we've got this broken down into this form, really we're ready to start substituting values. We know the force carried by each of the section, that's the F1, F2, F3, that's our work right here that we did in the previous video. We know the lengths, we know the diameter so we can calculate the areas, and we know the E value. And so we are in good shape. So let's just start filling this thing out with the actual values. The E value is 69 times 10 to the 9th pascals. It's 69 gigapascals down there. So we'll write it just like so. And start off with section 1 here. Section 1 is actually in green down below. You can see it has 3 kilonewtons. Notice it was in tension. And so here what I usually like to do when I'm working these problems is assume positive values are in tension and kind of use that as my sign convention. And so here I'll get it to base units and say this is my 3,000 newtons right here. The length of section 1 we can grab right here, 300 millimeters. That's 0.3 meters. Again, I like to get things to base units at this point. Okay, sorry about the interruption there. I had somebody at my door. So where were we? We were at F1 here is at 3,000 newtons. The L1 was 300 millimeters, or at 0.3 meters, and then A1. And so here, A1 is pi over 4 times the diameter 1, and D1 is 15 millimeters, so 0.015 meters. 0.015 meters squared. And so doing pretty good at this point. And so now we just need to keep filling out our values. Again, a lot of the stuff's already done as far as the hard work. I just need to find F2. F2 was 1 kilonewton. It's in tension as well, so I'm going to put that as a positive value. So that's 1,000 newtons. The length of section 2, that was the middle section, is 250 millimeters, so 0.25 meters. And then we have pi over 4, and what is the diameter of section 2? Section 2 is 25 millimeters, so 0.025 meters squared. And finally, section 3. Now, section 3 is our first one and the only one that's in compression. And so notice we have negative 4 kilonewtons here. I'm going to keep the sign negative here because I'm using the sign convention that positive means elongation, it means tension. And so here I'm going to have the negative 4,000 newtons here. L3 is 200 millimeters, so 0.2 meters. And we'll say that's divided by pi over 4. The diameter of section 3 was the biggest at 40 millimeters, 0.04 meters squared. Close our square bracket, and there we have it. As we'll say, this is approximately equal to some value. And so quite a bit to write. Just give me a few moments to get this thing entered into the calculator. Alright, so now we've got 3,000 times 0.3. And there's the denominator. On to the second term. And finally the fourth term here. And let's see what has happened, Slight error here in the beginning stages here. So give me one shot here to kind of redeem myself here. And so I'm pulling out the pi over 4, so I've got 4 divided by pi times 69 times 10 to the 9th. And then we'll say times 3,000 times 0.3 divided by 0.015 squared plus 1,000 times 0.25 divided by the 0.025 squared minus the 4,000 times 0.2 divided by 0.04 squared. And that looks much better. You can't really see what I'm looking at in my calculator, but the first time I messed up with the stuff outside of the square brackets, I ended up with a very large number, 3.38 times 10 to the 18th. That is a very large number. That should be interpreted as 3.38 times 10 to the 18th meters, and this is a decent example where you get something like that and you have to have some common sense about you and say, that can't be right. This thing is only, what, 750 millimeters long. 0.75 meters, that's not very long at all, and so this can't be 3.38 times 10 to the 18th meters. That's not plausible. And so that's where you start going back, look at your stuff you've entered in your calculator here. I just kind of fat-fingered something there, and it got off there. And so what I'm seeing in my calculator right now, that looks much more correct, is a value that says 7.196. Here, I'll get a little we'll say 197. Times 10 to the negative 5th. And since we're all in base units, all those units should work out to meters. Well, that's a quite small number, and it'd be more appropriate to think of it in millimeters there. And so this is also written, I'll say, which is approximately 0.07197 millimeters. Just multiply by 1,000 there, which is a little bit better. Oops, I lost it. So give me 1 second, bring it back. 0.07197 millimeters. So that means this thing elongated by 0.07197 millimeters. So if I was looking at it, I wouldn't be able to tell that with the naked eye here. I wouldn't be able to notice that it got longer, but it would have indeed. Looking at the actual problem statement to determine the displacement of the green plate, it'd be nice to tag some direction with it. Did the green plate go up? Did it go down? Well, here, since this entire thing is aligned vertically and it's getting longer, and I've got the fixed attachment point at the very top, that means this is actually in the downward direction. So the 0.07197 is downward, or if we want to talk about it as some displacement r vector, we'd say something like negative 0.07197 units would be in millimeters. And we'd say, hey, it's in the jth direction there if you want to think of ijk unit vectors. And that would be the answer to part 2 or task 2 of this problem. Also, we can go and look at this in terms of our SolidWorks model again. I did that with task 1. And so here is the SolidWorks model associated with the displacement. Notice I've got it to the displacement in the y direction, which is the vertical direction, the way our shaft's set up here. Units are in millimeters. Again, I can right click on my plot icon here, go to probe, I'll slide down to the bottom, click the very bottom of my section here, just go Control Z to get back to the isometric view, and you can see the value here is negative 0.073 millimeters. Negative meaning, hey, it went downward. The magnitude is 0.073 millimeters. Let's check that against our theory. Basically we had negative 0.072 millimeters here. So that's quite good agreement between our theoretical calculation and the numerical SolidWorks there. And so hopefully this helps you in looking at calculating the deformations associated with these axial loader rods. Again, sorry for the disruption midway through, and thank you for watching the video.